So far we have seen about graphs, basic terminology and what possibilities are there. Today we are going to talk about this breadth first search BFS and DFS. So what BFS exactly is, this is a simple algorithm that will find the shortest path, shortest route or path. You can have number of hops in between from a given node, say U, to some node V. Okay. So then what is the idea behind this? The idea of BFS is to explore the graphs in layers. Different layers are being thought and then BFS is carried out. How? If you want to go from say U to V, this is one node, this is one node, there may be many nodes in between. So layer 0 is the first node U itself, this node, right? So let us take an example also. This is an example. In this particular case, layer 0 is just node U. This is layer 1. That is the source. Then layer 1 consists of all nodes V with direct edge UV. Means if there is any edge between U to V, because we have to find out the shortest path between U and V, so we have to see that if there is, then that may be a shortest path. We have to include that. So this layer 1 consists of all nodes V with direct edge, means UV have a direct edge. In this we have layer 1. What are in layer 1? This is V1, V2 and V3. So from U to V there are these direct edges. So V1, V2, V3 they comes under they will be regarded on layer 2. Now coming to layer 3, or rather because this starts from 0, it is layer 2. So layer 2 consists of all nodes W. See, it is not U, neither W nor V, it is something else, W. It consists of all nodes W with a direct edge, VW. Now we are not talking about U, we are talking about the destination V. So any W which has a direct edge with the destination, this will play a part of layer 2 from some node V in layer 1. In this case, V1, V2 and V3 were in layer 1 and W1, W2, W3 they are in layer 2. Why? Because V1 is connected to W1, V2 is connected to W1, and in the same manner this W2 and W3 are also connected to layer 1, you can say like that. So we have to notice that V2 is already in layer 1. This V2 was already in layer 1, so we doesn't consider it to be in layer 2. And what about layer 3, 0, 1, 2, and then we have to talk about other layers also, because layer K it may go up to layer K, just not from 0, 1, 2, it may go to layer K. So what layer K has, it consists of all nodes W with a direct edge from some node V, means the penultimate or the previous one, previous layer. If it is connected to the next layer, then the layer will be formed. So layer 3 contains just X. Why? Because in layer 2 we have this W1, W2, W3, and only X is connected to any member of layer 2. That is why this X comes in layer 3. And what about this Y? We have to notice that Y is not reachable from U and is thus at infinite distance. Y cannot be reached from U. This is a directed graph, this is a direction, this is a direction, because we are talking about a direct graph. but this is a direction from y to x, so we cannot reach y from u. So we call it that it is at a infinite distance, and this is the recursive definition of layers. We recursively find out various layers. So it's not very difficult to prove that this definition nodes in layer k are exactly at distance k from you. Say 0, 1, 2 and like this up till k, the distance is k from you. And to implement this algorithm, we need to process nodes one by one. That is, as processing an entire layer which we have just found at once is not a standard programming functionality. So it has to go by layer to layer. And when we are trying to process nodes sequentially, we would like to make sure that all nodes from layer k that has been processed before we get to the nodes in layer k plus 1. What I mean by saying this, that all layer 0 need to be processed if I wish to go to 1, if I wish to go to 2, all layer 1 has to be processed. Since we discovered the node in layer k before those in layer k plus 1, we already done that, because only by knowing k we can go to, or we can find k plus 1. So this means we should process nodes in the order they were discovered, actually, one by one. And please recall that which data structure supports this kind of processing. This is first in, first out. This FIFO, first in, first out, is Q. This is the central part of your BFS algorithm. And to describe and to analyze, let us this dv, let us consider this dv to denote the actual distance from u to v, means d, this is for distance, and this square brackets dv, the distance the algorithm computes. This is the actual distance with round bracket. This is for actual distance which the algorithm is going to compute. So we hope that those will be similar, we expect, but we need to prove it actually. And we will assume that nodes are numbered with numbers 0, 1 till n minus 1, as I suggested that we start from 0. So till n minus 1 it will go. So we can just simply store values associated with nodes in an array of size n, right? We can store arrays or store values which is associated with the nodes in an array of size n. And also, in addition to this array of distances, which is dv, the algorithm will also compute an array of predecessors, the previous one, because we are talking about k, then k plus 1 layers. So algorithm will have to compute an array of predecessors, the previous ones, for each node v, which is not u. So this is a node in the previous layer which has an edge to your v. What I mean by saying this is, in this figure, we have v3, pw3 will be v3 and px will be w1, the previous one. Okay, previous one of x will be w1. Previous one of x will be w1, because we started with u, went to this v1, v2, then went to w1, then went to x. So x has a predecessor of w1. So px, the predecessor of p means predecessor. P predecessor of x is w1, and likewise. While this pw1 can have either v1, v1 and v2, because the layer v1 and v2 comes before pw1. And depending on the order in which these nodes were explored, it can be either v1 and v2. And we will try to consider the arrays as global variables. Okay, we need to keep our notation simple, so we will consider the array as global variables. So this is the actual implementation. This dn will store the distances from u. We want to go from u to v with the number of hops. Pn will contain or store the predecessors of node on shortest path from u. This BFS algorithm will do we have not no node is visited, so we start with be visited as false, and then we start with an empty queue, right? We start with an empty queue, and if visit is true, then we do something, and until this queue is empty, we peek front, then go to dq, and using some iterator, all nodes w with nh vw in e, and again we'll check for either visited or not, and if it is visited, we increase by 1, we go to next one, and again nq. So this queue already has this dq and nq functions available. So this is how we implement it. What is the idea of this algorithm? We start with just the seed u. We start with just u, and its distance from itself is obviously 0. Then the loop adds all the u's neighbor to the queue, and whenever we process a node v, means dequeuing it, we look at all its outgoing edges, and then the edge could lead to node we have already seen. What we have to do in this case? In this case, we should not process it again because it was already being processed, and if it did, we might accidentally increase the distance level. So if we have not seen the node w before, then we mark it as visited, so it isn't processed again. That is how it goes. If it is visited, then we have to see that we don't include it again, and set its distance and predecessor if it is not visited, and the predecessor to the node v from which this edge vw allowed us to discover the next, means from v to w. From v only we discover w. So the fastest way to go from u to w is to first go to v, then make more hop so that the distance is one more than that of v. Then finally what we do, we add w to the queue, and then it will be processed data. While we won't do a forward correctness proof of BFS right now, we would want to roughly think about how this BFS ensures correctness. And because we have discussed why FIFO queue is essential, we need to think that does it provide what we want. So a loop variant, again, as I suggested in our earlier discussion, a loop variancy has to be included that would work like this. So at each point in the while loop, which is this, in each point of this while loop, for all nodes v with visited is equal to tree, the value dv and pv are correct. What we mean that if because this dv equal to d cap v, so pv, the previous one, is the last hop node on the shortest path from u to v, and the distance of node in the queues are sorted. So let us assume that v1 to vk be the nodes in the queue sorted by when they were inserted. Of course, v1 has been in the queue longest, and vk has just arrived. Then the distance will be like this, and the node in the queue are all from just two adjacent layer, means the previous one. So while this may seem somewhat convoluted, if you can think about it some more cautiously, you will see how that captures exactly our intuition that this FIFO will give a close emulation of processing layers in the node wise layers. So this correctness proof would now we will establish this loop invariant by induction or iteration of this while loop. This is how it will go. Let us analyze this running time of BFS first. We see that the initialization of visited array while written as one line, as you see in the code, visited means only one line. Okay, actually this is the code this is the line from where the code will start. So this particular line we are talking about, and we'll subsequently talk about each of these lines. So this was one line only where visited. Actually, it takes order of or theta of n. Then all other individual commands take this theta of n. So we'll analyze loops inside out because we have used for loop also. This for loop goes through all outgoing edges of node v, and in our iterator, which is implemented, we use an adjacency list for our graph. Then this takes how much? If we use adjacency list, I hope you remember about adjacency list and adjacency matrix. So this takes around theta of outer degree for some node v, and all the other code inside while loop will take only theta one time. So the total time inside one iteration will be theta 1 plus out degree, and we'll drop this one. We'll keep ourselves to this theta out degree. Why we are keeping it 1 here? The reason is that for the moment it is possible that this out degree can be 0, so we need at least something inside, in which case our analysis would claim that the iteration takes 0 time, which may not be true. That is why we are keeping it 1. And we notice that the while loop may rule or run over all nodes, so the running time is a sum. How? This will be sigma theta 1 plus out degree, and sigma for both of them will be, this will be n, this will be m, and this will be together theta n only. So the total running time of BFS will be theta n plus m, which is linear in the size of the graph. That is why BFS is a fast algorithm. The time it takes just to read the graph as input. Hope this is somewhat clear. Even if you don't understand, you can understand 10%, that will be good, because once you read it again in your textbooks, you will see what I was talking about. Then we come to this DFS. We have seen BFS. BFS processes the graph by layers of increasing distance from a certain start node. We assumed it to be U, and that is why we assume that FIFO would, or FIFO kind Q will be quite great to implement it. But there is a downside of BFS. Such algorithm jumps all around over different areas of the graph. Searching will just jump all around. For example, if you want to trace the execution on the graph we have just seen in 20.1, we see that after processing U, V1, V2 and V3, rather than staying at V3 and its neighbor, the algorithm jumps to W1. Okay, it has to go to the next layer or in the neighbors in the vicinity, but it jumps to W1 because we are applying BFS way to get those layers. So when we want just shortest path, that's of course not a problem. But sometimes you want to explore a graph by staying local, not jumping here and there. This is sometimes needed as a part of other algorithm. And to just explore locally the graph, we would want to first explore all the nodes around V before actually switching to any other part of the graph. And we can accomplish this by replacing this FIFO Q in this BFS, which was the core or heart of our BFS, with LIFO stack, last in first out stack. In this manner, the most recently added node will be the one which is explored next, which will ensure that the algorithm always stays in the neighborhood of the node. Just by one word change, the algorithm is exactly similar. Means BFS and DFS both are almost similar, and we call it as DFS because it first explores the neighborhood of a node, going deeper into the area before actually going for other parts of the graph. And DFS will not find shortest path, maybe because in figure 20.1 we have just seen, it will first reach V2 from V1, assigning it a distance 2, and never revisiting this choice, because in that particular case we have to revisit it, and DFS may not. And this is fine. DFS is not used when one wants shortest path. DFS is when you need a shortest path, you have to go to BFS only, not DFS. But since this DV values don't really capture anything specifically usual anymore, in this case, we would simplify the algorithm by removing the arrays altogether. As we have known, the running time of DFS is order of or theta of n plus n. Since we just plugged in one data structure in for another, and all operations take the similar amount of time, what we have done, replaced queue, entered LIFO stack. So this is an alternative implementation of DFS, which is using your recursion instead of your stack. We just start with visited n, this is an array, false, DFS, and until means you use an iterator if visited. If we are not visiting to V, all nodes V with an edge UV, and then we again call DFSV. So in this kind of implementation, we don't have to explicitly worry about this stacks. The recursion automatically will take care of the stack. So this was about our DFS and BFS. Hope you can just understand and try more learning about, because this is very important as far as shortest path algorithms etc. are concerned.